Challenge, please.
We would like to challenge problem 5, dancing slinky.
What?
We reject.
Reject.
We would like to challenge problem 1, paper boomerang.
1.
We reject.
Reject.
Okay. We would like to challenge problem number 3, Lato Lato.
3.
We accept.
Right. Presentation. Name. On a table. Please.
Honorable Judge and awards the opponents. I'm from Team GGWP, and my problem is number 3, lato. This is our problem statement. Attach a ball to each end of the string and connect the center of the string to a pivot. So when the pivot oscillates along the vertical direction, the ball starts to collide and oscillate with an increasing amplitude. So we're now going to investigate this phenomenon. We're focusing on 4 points: energy distribution and the equation of motion, and how initial conditions impact the motion, and also conditions for stable and unstable state of lato, and stimulation versus reality. This is the phenomenon. We let the x be this direction and the y be this direction. And the theta is the strings, the angle between the strings and the y direction. So our observation and assumptions before doing our experiments, we observed that the slack occurs during the second phase of the motion. The second phase defines here as the collides at the upper point of the lato. And we consider a pseudo 2D motion, and somehow it reached a dynamic equilibrium. So we assume that when the oscillation frequency is in line with that of the natural frequency, the amplitude will increase. And there's a negligible horizontal motion of the pivot and a z-dimensional displacement. So here we let the c to be zero, to be z displacement minus its original z displacement. So if the c is smaller than that value, we'll let it to be a 2D motion. Here we can consider that in the initial state of a lato is actually a 3D motion, where the c is only this small. But in later experiments, we'll wait until it reaches a 2D dimension, where the c is smaller than this value. So all the discussion later is only about 2D model, about the energy distribution. To begin with, we consider the oscillator as like a simple harmonic motion, where the work done by it can be shown as this. Also, we consider an inelastic model, where the kinetic energy before and after the collision can be shown as this. So ideally, the energy transmission of one ball can be denoted as below. The potential energy plus its kinetic energy plus its damping will equals to the work done by the oscillator. So next, we want to consider torsion during the motion. So the work done by torsion can be denoted as below. But there is no obvious torsion or rotation of the ball when we observe it. So here we only discuss the order of magnitude. So since it's impractical to directly measure the angular acceleration of the ball, we will demonstrate that its influence is negligible by assuming an extremely large value for it. Here we let alpha to be 100 REP second squares. And we can see that after calculation, we can see that the work done by torsion is that small. So we will neglect it in the later experiment. So to conclude, the work done by torsions is far more smaller than the kinetic energy or the potential energy. And about the equation of motion. As I mentioned, I consider an elastic collision, where the angular velocity after the collision can be denoted as this. So it can be simplified into this equation. So using the law of energy conservation, the derivative of energy equation can be shown as this, where gamma is the reciprocal of the time constant. So to conclude what I have said above, this is our equation of motion. Our preliminary experiment. This is our experiment setup. We use a mechanical linkage to let the pivot oscillate only vertically. So we want to first demonstrate that our motor has a constant frequency during the experiment. So here we consider that we use a random frequency of the oscillators, then use tracker to track it, and we see that this is a perfect cosine or sine wave-like graph. And where in this sense, the t is about this small. So about the next experiment, we want to consider the damping coefficient. But if we use this equation to calculate it, the error will be too big, so we consider its natural log. And we will take its negative slope of the graph, where we can see that the gamma is 0.1 about. And the restitution coefficient, in order to get the restitution coefficient, we release one ball and goes at 90 degrees, with another ball staying at the initial position, where it's 0 degrees. And we record the short time interval while colliding and calculate the coefficient, where we have the coefficient is extremely large. Experiment, we want to demonstrate the energy distribution. The relevant parameters is string length, amplitude, initial angle, and initial angular velocity, but it's always fixed to 0. So for time constraints, we are going to provide one data, but that simplifies all those 18 trials we conducted. So this is the numerical solution of the equation of motion I mentioned before, where the initial angle is about 10 degrees. And this is our experimental results. We can see that the theta actually oscillates between 0.025 and 0.09 RAD. And the theta will not reach 0. Damping here is imperceptible since the amplitude doesn't change that much. And the same period is observed with the oscillator. So the possible deviation here is the string is not always taut during the motion, so making the peak of the angle less than we expected in the numerical solution and the data we collected. And also at the lowest part, the angle will not reach 0 due to the radius of the ball. In numerical solution, we consider the ball as a point mass, so there is no radius to consider. And the oscillator provides energy to replenish the energy loss, causing the peak to maintain. So this is the energy concerned in all the data we collected. So for the qualitative analysis, we're seeing that damping cannot be observed in the experiment due to the oscillator. So energy loss is mainly caused by the vibration. So when the energy loss is bigger, the work done by the oscillator will be bigger. And likewise, the energy loss caused by the inelastic collision will be replenished. And here we provide an energy distribution about the pivots throughout the entire motion. The following equation should be fulfilled according to the energy conservation. Work done by the oscillators will equal to the kinetic energy, potential energy, energy loss done by the damping, and energy loss by the vibration. So to calculate the potential energy and kinetic energy, to find out the work done by oscillators in one stable period, where each period the work done by the oscillators is different, we are going to show you how to calculate it in one sense. So in the experiment two, we're here to justify our equation of motion. This is our equation of motion, and here we put in our 18 trials data into it, and we calculate the average error, and we see that error is extremely small. For the experiment three, I want to investigate the connection between frequency and amplitude. So here we aim to find the optimal frequency that such amplitude reaches its maximum during the same length. Natural angular frequency of the single pendulum is denoted as omega 0. And in our sense, we let omega 0 to be 8.75, where L is equal to that value. So here we consider a form of differential equation that is similar to our equation motion, which is known as Matthew's equation. So in the U part, it means unstable, and the S part, it means stable. We let epsilon to, if we rearrange our equation of motion to let it fit this form, we can know that the epsilon is equal to that and the delta is equal to that value. So we first consider an undamped and a small angle model, and also a small epsilon. So we can see that in P1, the unstable part and the P2 stable part, there have a significant difference between the angular. We define the later experiment that the P1-like motion, where the angle possesses an exponential growth. And on the other hand, we define stable as P2-like motion, where the angle has a quasi-periodic behavior in time. So this, we will later consider a Q1, Q2, Q3 to investigate the phenomenon. This is our relevant parameters. And we can see that in this experiment, this chaotic system will occur. And due to time constraint, I will put it later. And for an unstable part, we can see that it can reach its upper point and collapse there. But for the stable part, it can only stay under the semicircle. So now we include damping in our series, so we add this here. So we consider damping as 0.2, 0.1, and 0.05, and compare it to the undamped graph. We can see that the stable part of the graph is even bigger. And for this part, you can see that about delta equals to 2 and 3 there. There is a significant difference. So after analyzing certain conditions for our Matthew equations under small angle approximation, We here plus lateral cannot use a small angle approximation. Therefore, we consider a Taylor series about sine theta. So we expanded and we have this expansion about called Matthew-Duffin equation. We find that period doubling and cyclic fold bifurcations may occur, whereas a typical way to get into a chaotic system. So we are not going to explain why we are now going to explain why the amplitude increases when plane lateral in reality during this equation. This is our Hardening-Duffin equation oscillators, which can be shown as this equation, and there is the initial conditions. We can see that actually the frequency has something to do with the amplitude. So when the amplitude, in reality, to maintain stability, we will unconsciously alter Hence frequency, which cannot be recreated through our experiment. So possible deviation here is when the amplitude increases, the frequency will not maintain the same, making the ratio between natural frequency and the frequency of oscillators alters, which means the delta in the previous equation will change. As that occurs during the second phase, may cancel out some of the energy input, making the motion to be more unpredictable and more susceptible to initial conditions. So to conclude, this is our energy distribution equation, and this is our motion equation. And this is our energy concerned in the whole experiment. And the biggest conclusion is that not every frequency can reach a stable state. Likewise, not every frequency can reach the second phase of lateral. Only when certain conditions are fulfilled can phase 2 be reached. And namely, if provided a harmonic oscillator where omega is constant, it can never maintain in phase 2. This is our reference, and the data collected is in this paper that the graph showed in the previous presentation. That's all. Thank you.
Component phase.
Well, does the gravitational acceleration contribute to the increase in amplitude of the lateral?
Can you explain again?
The gravitational acceleration,
Well,
does it contribute to the increasing amplitude?
yeah, we consider it in the potential energy.
Okay, thank you. Can the increasing amplitude be explained by the constructive interference of the oscillations?
Constructive interference, yes.
Okay, thank you. Does the system rely on the resonance effect to sustain the increasing amplitude?
Yes.
Does the oscillation frequency of the pivots directly affect the collision frequency?
Directly.
The pivots oscillations,
Uh-huh.
does it directly relate to the oscillation of the lateral?
Oh, yeah.
Well, the both fail to collide if the oscillation amplitude is below a certain condition.
The ratio, I would say that, not a certain value. I would say the ratio between the frequency and the natural frequency, which is mentioned in the delta.
So there is a specific value
Yes.
of the ratio. Thank you. Does the rate of the energy transfer between the both increase as the oscillation amplitude grows?
Yes, as I mentioned, in every cycle, the work done by the oscillator is different. So we provide a method to calculate one cycle in our experiment.
Thank you. Can the oscillating pivot's acceleration directly influence the energy gain by the ball?
Energy gained by the ball.
Yes.
Yes.
Does the pivot's thank you. Could the pivot's materials properties affect the stability of the vertical direct oscillation?
We did not discuss this in our presentation.
Can you predict what might happen
You mean the
when we
different
change the different pivot's materials? Will it
pivot
affect?
materials?
Yes.
No, I don't think so.
Well, adding mass to the balls decrease the amplitude growth.
Well, adding mass
To the
The-
laterals, well, it make the amplitude growth decrease.
make the amplitude growth decrease. No.
And can an unstable pivot's motion disrupt the regular collision pattern? Unstable pivot's oscillation.
Time's up.
No, our pivot oscillation is all the.
Thank you. of the juries, the opponents would like to speak. Honorable juries and fellow competitors, and the opponents from Team Self here. Today, I'm going to oppose problem number 3, lato-lato. This is a problem statement, and we will mainly focus on the mechanism behind the increasing amplitude, and what parameters will affect the amplitude of the oscillation. And this is the reporter's outline. The reporter's theory mainly used the law of energy conservation, and he provided a very clear collision dynamics through the theory and formula and simulation. And he also mentioned the dissipation of the torsion can be ignored. And about the resonance, we think that's one of the main factors that creates the influencing factor. And about the reporter has mentioned in a short answer, it will also be one of the influencing factors to the experiment. And also, the reporter thinks the lato-lato's dynamic motion will be in a simple harmonic motion. And about the experiment and analysis, the reporter used the connection between the oscillation frequency and amplitude as one of the parameters. And the pivot movement is one of the influencing factors we want to discuss later. And about the lato-lato energy distribution, we think the reporter gave a very clear distribution and explanation. And about the force and rebound behavior is also one of the parameters the reporter has done. And about the coefficient of the restitution, we think that's one of the important influence factors due to the increasing amplitude that the problem statement has mentioned. However, about the controversy and the deviation, we think the energy dissipation during the oscillation is also one of the influencing factors need to be considered. And the unexpected deviation in frequency and amplitude under specific condition is also one of the things we want to discuss later. And now let's talk about the strong and weak points for the reporter. The reporter provided very well analyzed the increasing of the amplitude of lato-lato, which perfectly matched the problem statement. And he gave a phenomenological explanation, detailed it, and a detailed theoretical derivation. However, he didn't analyze the change of length during the process because the length of the process might be changing during the oscillation process. And the theory limit is ignored. And there's lack of specific parameters that control the oscillation of the parameters. And there is lack of error and deviation explanation, and lack of error bars, and of course the theory line. However, the reporter has mentioned one very important influencing factor, which is the stable and unstable condition for the lato-lato. And this is the point we want to discuss. First one is the force analysis, which is the impact force between two lato-latos balls. And we will mainly talk about the conservation of the momentum and the energy loss during the collision. About the tension force, it's about the strain of the lato-lato. We want to discuss how does the tension change during the process and the length of the swing angle. We want to know that if the reporter has done the experiments to do this. And the second one is the data analysis, which talk about the amplitude, frequency, effective acceleration, angular velocity, collision. And about the parameters, we want to discuss the frequency, length, materials properties. And materials properties, this includes the materials of the lato-lato and the mass of the lato-lato and the different elastic coefficients. And about the possible error, we think the length variation will be one of the influencing factors. And the uneven impact force and the releasing method is one of the influencing factors we want to know. And about the lato-lato's motion, we will talk about the double collision dynamics. And the pendulum-like motion, we want to discuss is the reporter consider the gravitational acceleration and the vertical acceleration in the experiments. And finally, one of the most important parts is the energy transfer. And now I would like to invite the reporter to give this discussion. Can you turn to your page 26?
Yes.
Well, I noticed that there is a sine theta. Is the sine theta represents the pivot oscillation?
We derived this equation since our.
Well, we would like to know what is the sine theta
Sine theta
represent in the experiment.
In our experiment setup, we said that the theta represent the string of the lato-lato and the y dimensions, the angle between them.
So you think that's a sine wave?
Huh?
You think that's a sine wave?
No, that's a second derivative equation, so we did not consider it as a sine wave.
Can you please turn to the page showing the pivot oscillation?
Pivot oscillation?
Yes, thank you.
You mean the experiment setup or
The chart showing the p-value oscillation.
the preliminary experiment, right?
Yes.
This one?
Yes.
Okay.
And the opponents would like to know if the reporter thinks it's a sine wave or a triangle wave instead.
I think it is more like I don't know, maybe a cosine wave.
The reason why the opponents ask this is because in our opinion, we think the equation in the reporters has provided maybe represents the oscillation of the p-value. And since you use the sine theta, however, we
We
think
didn't use
this,
sine theta in this graph.
well, we think that's kind of related.
No, that's nothing to do with that. This demonstrates that our statement, previous statement, that the oscillators we use in later experiments has a constant frequency.
Yes.
Only demonstrate this, that we can make sure that the frequency will not be influenced by the mass of lateral. Because if the mass of lateral is too heavy, it will not, when the pivots go down, it will be quicker. And when the pivots go up, it will be slower. So this has nothing to do with the sine wave, but have to do with that we want to demonstrate that frequency is a constant.
Okay, thank you. So do you consider the p-value oscillation in the equations?
Of course, if the pivot don't oscillate, no energy input, then no lateral.
Yes, because the reason why the opponents ask this is because the wave of the p-value is important to the equation. Now this is we think in our opinion it looks like a triangle wave, and which is the many sine wave and add together. So does the reporter think of this part?
No, because we use a mechanical linkage where it oscillates like this. So it's actually this only up and down.
No, I
No
mean,
triangle wave is occurring.
may we use the blackboard? The sine wave I mean is like this. The p-value of the oscillation.
The pivot of the
Oscillation. The oscillation of the pivot.
the oscillation of the pivot.
And we
What
think
graph? What to what? What's your?
this is the p-value motion like you have provided.
Oh,
And we think this triangle wave maybe one, because as you can see, the curve here is different, which means it has the faster angular velocity.
Oh no. That's just about the arrows, okay? No, because you cannot have a concise or you cannot observe a perfectly sine or cosine wave. That's just something to do.
So the reporter has considered the wave in the equations. Is that right?
Yes.
Okay, thank you. And can you please draw the force diagram of the lateral?
Force diagrams.
Yes.
When you go up or down.
Can you please draw the both? Thank you. Can you please explain the energy transformation during the oscillation process?
Okay. Let me use another color.
Okay.
So when the pivot goes upwards, okay?
Okay.
So there will be an energy input.
So in this condition, the laterals will tend to collide.
Yes. The lateral always collides at the highest part and separates at the lowest part, as shown in the phenomenon part.
Well, can the reporter please demonstrate the phenomenon?
Okay, but I want to say that first, this is a lateral in reality, which we consider in experiment 3 is different in our theoretical model. Because in our theoretical model, we consider the oscillator has a constant oscillating frequency. But if I do it with hand, I can never do that.
Well, can the reporter, since the lateral is a worldwide toy that plays around the world, and can you please explain the theoretical model you have mentioned and the comparison with the real life conditions? Can you please demonstrate how to play the lateral?
Oh, just to demonstrate how to play it?
Yes.
But your screen is so small. Like this. This
Yes.
is the first stage.
And as the reporter has mentioned, the theoretical model didn't match the real life condition.
Yes.
How did you put the dissipation or the
So we
modify
consider
in the...
we consider a hardening ducting oscillator, where the oscillation of the pivot oscillation, the oscillation of the frequency will change during the time,
Yes.
where it has a frequency, have something to do with the amplitude and the frequency. So in reality, if we play lateral, we know that in the first stage the amplitude is small. So as the amplitude increases, the frequency changes. That means
Short answer, please. General answer, please.
as amplitude change, frequency change. Frequency change, the frequency between the oscillators and the natural frequency change, which will not maintain a resonance system.
Okay. Have you compared the manual conductance to the theoretical model? The wave, yes. Have you conducted?
I think theoretical model needs to, because we want to first discuss if we fix this.
Yes. Have you considered the situation? Once I have the, for example, the up and down collision, is the wave compared to the theoretical model is the same? Up and down collision condition. Have you do the experiments to compare the different waves for the reality and the theoretical simulation?
Oh, as I mentioned in my conclusion, if a provided harmonic oscillator where omega is constant, it can never maintain in phase 2, which means I cannot make sure it will polarize in this like chaotic system. So I cannot make sure that this will always happen. So this will only happen in a short time interval. Because when you play this in reality, it's actually a 3D model, not a 2D we assume in our...
However, the lato-latos is a relative condition. How can you, like, in the lato-latos is played widely around the world. How can you use the theoretical model to describe the phenomenon in reality?
So again, use the hardening buffering.
However, like, as you can search on the anywhere, the lato-latos is widely played with the up and down collision. So, have you any thoughts about the up and down collision compared to the theoretical model you have shown in simulation?
So I want to reiterate again that you oscillate ups and down. This phase, second phase, has something to do with your oscillator.
Yes.
So when you manually play it, you can use a brain to change your hands that makes it resonance to maintain it in the second phase. But in mechanical linkage or any machines done in the experiment, we cannot change it. We cannot instantly observe the frequency and instantly calculate the ratio between its frequency and the oscillators.
Yes, can you please turn to the page of the simulation?
Simulation?
Of the up and down collision. Thank you.
You want chaotic, unstable, or stable?
Up and down collision.
Up and down collision?
The simulation of the up and down collision.
Yes, it includes a chaotic or an unstable one. This both collide in up and down.
The unstable one.
Okay. This one.
Yes. Can you please explain the difference with the real life condition?
This oscillator is oscillating in a frequency fixed in this value. But in reality, we cannot fix our hands frequency. Again, we cannot fix. If you can, you are godlike. Okay?
I get your point. And where does the energy dissipation mainly come from? Which one do you think contributes the most?
Energy dissipation?
Yes.
I consider it, I will say it's the vibration of the string. Because when we crack the balls...
General answer, please.
Okay, the vibration of the string.
And can you predict in which condition can your theory be put to use?
Put to use? My theory can be put in use in all the models. Like if we want to observe phase 1, which is down there, we can use a small angle one.
Do you have a range for it?
With what's in range?
For the ratio you mentioned in the short answer.
Yes, we can see that the ratio is actually epsilon. And we have a graph about epsilon and delta. So in the gray part, it is actually an unstable part. And in the red line is a chaotic one. And in the S part is a stable one.
Okay, the opponents would like to clarify what is the mainly influencing factor for the increasing amplitude? What is the main influencing factor to the increasing amplitude? The opponents would like to clarify.
Okay, so...
Time is up. Conclusion, please.
Well, in the discussion summary, we have mainly discussed with the reporter about the definition of sine wave. However, the opponent still thinks the wave of the pivots need to be considered since there is an obvious triangle wave compared to the sine wave or cosine wave the reporter has mentioned. And about the chart showing the triangular wave chart and sine wave is different. And about the opponent thinks that there are differences in the theoretical model of the lato-lato and reality. The opponent suggests the reporter to compare what is the real difference between the real condition of the playing lato-lato and the simulation and the theoretical model, especially in the up and down collision, which is one of the most important parts of the lato-lato. And the last one is the energy dissipation is mainly caused of the vibration of the spring. Since we didn't really discuss, so the opponents would like to clarify here. We think the length during the oscillation would change. We think the reporter should do the experiments on clarifying the length of the pendulum. And that's the end of the discussion summary. Thank you.
Why do you think this related to text? It's you. Why do you think that's connected to the triangle wave?
Because the chart that the reporter has provided, it looks like a triangle wave. And since the reporter has mentioned that the width of the pivots is important for the lateral dynamic motion, so we think that the pivot's motion is really important to discuss.
Do you think so, or you have another opinion?
I disagree with him. But instead, whether we are wrong or correct has nothing to do with this. We are not just going to demonstrate that in our later experiment, the frequency is a constant, where we can compare it to the reality, where the frequency will change by our mind. So we can play it lato-lato in reality, but not in simulation.
Okay, can you turn to page 53? Can you explain what this formula comes from?
Oh, this is the potential energy, change in the potential energy. Change in the kinetic energy, and this is the restitution coefficient. Damping caused by the damping during the motion, and the work done by oscillator with the input, output. And this is when we consider its derivative, we can have this equation where we need to substitute the angular velocity when the ball collides. We can show it in this graph. We can see that actually when the ball collides, because we let the direction here to be positive. So it actually goes to positive and back up, because the restitution coefficient is extremely large, right? Like 0.96. So actually it's only the direction of the velocity changing. So you can see that this two lines is like parallel to each other. Right, about 0.8, and when the ball collides, you will change the direction to a positive 0.8 velocity, and then go down again.
And this formula, can you explain?
This formula is the same with the previous bit, where n represents the mass and amplitude omega. Here we consider a harmonic acceleration, like the acceleration done in the harmonic
Is up.
position.
Reviewer, please.
Okay, according to the this problem statement is about the balls that attach the ball to each end of the screen and connect the center. This phenomenon, and they investigate this phenomenon. And what the report said, he explained the web of the opponent, and he do the lapo in 2D simulation, and he explained the y line is not 0 in his report. And in his experiment, he used the same amplitude and frequency. He fixed them, and he measured the data from the experiment. Further, his pros and cons, he fixed the amplitude and fixed the frequency. And he do many experiments and measure what's the data. But I have some suggestions for him. He need to fix the method in the formula to make the audience know how much actually is trend. And second, don't talk about the difference between the pictures, just explain the trend. And for opponent, he explained why that next picture connect to the triangle web very clearly. But I have some suggestions for him. He needs to focus on reporter's reports rather than asking what reporter did not focus on. And he did not ask the reports to calculate the data and the relationship between formula and the experiment. And further, in their discussion, I found that there are some mixed. Because in the real world situation, how do you make sure 2D is same as the 3D? Okay, thank you.
Reporter conclusion, please.
Okay, to conclude, I and the opponent discussed about whether the reality and our experiment fits. And in our opinion, we did not use in our first experiment where he thinks that it is a triangle wave. Here we demonstrate that we only want to demonstrate that it's a fixed frequency. And in reality, the amplitude has something to do with the angular velocity. So if your angular velocity is not the same, which means the ratio between the angular velocity and the natural frequency will not be the same. And will make the delta in the Matthews equation difference, which means that you can reach a stable, unstable, or even a chaotic system, which is a huge difference in simulation, experiment, than in reality. And also the reviewer says that I need to compare the reality, this one, and the experimental one. We can see that I compare it to see that the maximum amplitude is actually shorter, which makes me think that it may be this energy loss maybe is come from the energy loss, like the vibration of the spring or damping. And also, the opponents suggest me to do different lengths, but I want to reiterate again and again. I do 18 trials with different lengths. So I did consider this in our parameters. We changed the length, we changed the amplitude of the oscillators, we changed the initial angles. We only fixed the initial angular velocity when we release the ball with a machine. Okay, and the formula deviation map in page 53 is something to do with the reviewer, and I think that I've clarified it already. And the comparison between experiment and reality is this actually will be flipped out because we only investigate one ball. So this simulation, we cannot only fix it to one ball. It actually goes to the 1 and 2. So you need to flip it up from the x-axis and flip it up, and this will be matched to the graph.
Time for jury. Any question or comments? Please.
The reporter, you assume that's an elastic model, right?
But the coefficient is really big.
How about if you change it to elastic?
How about if I change it to elastic?
Will that still work?
In our equation deviation, we consider E. So I think if it is elastic, means that the E is like 1. So which means that the energy loss caused by the collision can be ignored. So the energy loss will like majorly will comes from the vibration, because the spring, when the ball collides, the spring actually vibrates because of the inertia. When once you go this collides and the ball, the spring here.
Okay. Just point out what caused the lateral motion, side motion.
Oh,
In the beginning.
in the beginning.
Yeah.
Oh, we changed the initial angular.
What force?
Huh?
What caused the lateral motion?
Lateral motion.
Yeah.
Because like when in our experiment, the radius of the ball is extremely smaller than the length. So it's actually, if you use a slow-mo camera to investigate it, it's actually a horizontally collides, because the ball has a extremely, compared to the length, has an extremely low radius. So it's like 2-point mass colliding, and the string will the ball.
But there is no gap between the ball in the beginning, right?
Yeah. So in our simulation, let me separate this in two parts: a reality one and our experiment. Okay. In our experiment, we get a initial angle because we assume it to be a 2D.
Why initial? Why initial?
Because in reality, when we play this, it is actually a 3D, right? So it will have this z-dimensional motion. So when this occurs, which means that friction will cause here, which means that they will get energy. You can see that if you want to play, you can see that when you oscillate this, the first time will never be a 2D, perfectly 2D motion, where the center of mass of the ball is not in the same plane of the pivot. So it's actually this collides and will in z-dimensional displacement will occur. So this will gain it in energy.
Okay, so will you two agree with me?
Well, I agree with the reporter. However, we think the initial condition of the playing lateral method need to be considered. Like in real life, like the demonstration the reporter had provided, as you can see, when you start to play the lateral, the rulers will have the big staggering, and that's one of the parameters to that's one of the factors to successfully to make the lateral start to collide. And after the big staggering of the lateral, it will have a stable pattern, like the reporter has mentioned in his report. So we think that's a very important force analysis. We need to focus on the initial condition.
What about you?
shoot catching. For 3. What happened when the string is loose?
Oh, like the opponent just answered the jury. He thinks that in my experiment, I don't think that the string will be smooth during the down semicircle, because we calculate like this is the pivot, the velocity of the pivot, and the ball's velocity is both changing. So we make sure that we calculate it and we find out that when the ball goes down, and this goes down too, this string, the velocity of this ball is always high.
Thank you. A short answer is okay for you.
Can you rephrase?
What happened when the string is loose?
During the collision process,
Yeah.
the collision will be valued since the collision is not perfectly made. The string is not like in this condition. We will call it stable. And what if today become this? The lateral phenomenon cannot be generated.
At the beginning, its line will not be straight. Yes, and I think the spread is not much.
Thank you. Because the time is limited, maybe we go to the marking line. Thank you. Ball reporter. 7, 8, 7, 9, 8. For opponent. 7, 7, 7, 8, 6. For reviewer. 4, 5, 5, 5, 5. Thanks for all. Please return by 10:40.